Hello, welcome to Profiles here on the UCF channel. I'm Ed Highland, and today we're going to ask a simple question: what is light? The answer you will discover with us is not so simple. Our guest today is Dr. Peter Delfyett. Dr. Delfyett joined the faculty at the School of Optics and the Center for Research and Education in Optics and Lasers, CREOL, at the University of Central Florida in 1993. He has published over 275 articles in journals and conference proceedings, and among his many honors, he was awarded the 2001 Pegasus Professor Award, which is the highest honor that the University of Central Florida can bestow. Thank you so much for joining us today, Peter. The question of light, it's all around us. Why is that something so important for researchers to delve into?
Well, Ed, that's a very interesting question. We as humans, as you can tell, are literally visual human beings. Everything that we do and as how we interact with the environment is through light. Of course, we have sound and touch, but we are literally visual creatures in my perspective. And so the study of light not only is important in terms of being able to understand us better as human beings, but there are so many other important technological applications of light, whether it's for medical industries, computers, communications, etc.
We talk about light as something you can see, but now it's being utilized in terms of things that perhaps we can use to hear better, to transmit intelligence and data and communications. So light is a multifaceted creature, is it not?
That's right. As a matter of fact, typically people like to view optics as an underlying discipline, not as a study of research by itself, simply because light is used as a part of so many other different things. As an example, light is used in your supermarket scanner. We have lasers in your compact disc player, inside your computers. Concepts of light are used to make people see a little better. So it is effectively an underlying technology or discipline that feeds into areas of biology, physics, chemistry, engineering, etc. But what we're really doing, which is neat at University of Central Florida, we recognize the importance of optics and photonics, and the university has decided that the field of optics should be a discipline in its own right. And as a result, they established initially a CREOL, the Center for Research in Education and Optics and Lasers. Then we became the School of Optics, and now we're the College of Optics and Photonics.
Well, let's get specific. Let's talk a little bit about what you're doing with light, and in specific, some of your laser research. What are you up to these days?
We're doing a variety of things. Obviously, one of the things which is nearest and dearest to our heart is the use of lasers in terms of transmitting information from one point to another. And one of the recent things that we did was to develop a very small, tiny semiconductor laser. And the semiconductor laser is a device which is about the size of a grain of sand or a grain of sugar, or whatever is your favorite grain. But the feature is that with this device, we can make the laser turn on and off so fast in terms of producing blinks of light, kind of like Morse code. The light is on, that's a dot. The light is off, that's a dash. So with this we can send information, but the most important thing we did is that we showed that with this small tiny device we could send over 1 trillion bits of information in 1 second from this tiny device that basically can sit inside your cell phone or your laptop computer.
Now, where can we go with that? I mean, obviously, if we're talking about miniaturization and things that are in a cell phone or a laptop computer, what kind of other applications are going to link us all together in that fashion?
Sure, excellent question. Normally, when I say numbers like terabits or trillions of bits of information, megabits, gigabits, terabits, everyone's head starts to spin. It's like all of these words. What does it really mean? So let me see if I can break it down a little bit, and that will certainly point to some potential applications. A terabit of information, sending a terabit per second, would be analogous to trying to transmit 25,000 cable TV channels to your house. That's one example. Another example is that in a second, a terabit of information would allow you to download 3 full-length 2-hour videos from your favorite video store in a second. So after 2 seconds, you could have 6 full-length 2-hour videos. After 3 seconds, you'd have 9 full-length 2-hour videos just coming into your computer at such a breakneck speed. Now, obviously, you'll say, gee, who really needs that? 25,000 cable TV channels, I'm just happy with the 100 that I have.
I can only watch one movie at a time.
And I can only watch one movie at a time. I don't need to download 3 in a second. But the nice scenario I like to try to promote this idea of high bandwidth connectivity is the fact that many people use their computers to work on the internet. And many times people like to point and click on something and they have to wait for the download. And it typically takes a lot of time. And the numbers I typically like to use is that when people use their computers to talk to the internet through a standard dial-up or modem, they're talking to the internet at maybe 58,000 bits per second, and your computer may run at about a gigabit per second, a billion bits of information per second. Now that means your computer is running 17,000 times faster than what you're talking to the internet. So let me put that in perspective, and then I'll kind of close the loop for applications. We all know, since we're all good Central Floridians, that the space shuttle goes around the Earth at 17,000 miles per hour, and a newborn baby will probably crawl around on the floor at about 1 mile per hour. So the space shuttle goes 17,000 times faster than what this baby crawls on the floor. So if your computer runs at a gigabit per second and you talk to the internet at 58 kilobits per second, again, which is a factor of 17,000, when you buy your computer and talk to the internet, it's like you went out and bought the space shuttle and are limited to driving it in your driveway at the speed at which a newborn crawls on the floor. So this is clearly a problem. And so this is why when people point and click on the internet, the download times takes quite a while. So if you ask people, gee, wouldn't you like to be able to point and click on something and just have it immediately appear, just boom, in front of your eyes? Everyone is willing to sign up for that. Now, in order to make that a reality, you really need to have the connectivity between your computer and the internet and other computers to operate at the rate at which the computer engine itself is running. And so if we stop and think about this for a second, just at University of Central Florida alone, we have about 40,000 students. And if everyone were to have a computer in their classroom, learning information from their professor and trying to do interactive type activities through the internet, with 40,000 students and each one wanting to have internet connectivity at 1 billion bits per second, we would literally need information handling capabilities at UCF of 40 trillion bits of information per second. And this 25,000 cable TV technology is already 40 times too slow. So yes, we can only watch one movie at a time. We don't need 25,000 cable TV channels. But when we think about a major metropolitan university like UCF and being as wired as we are, we really will need to have this type of terabit per second technology as we advance towards the future.
I'd like to talk about the infrastructure involved in attaining those speeds, but first let me take a giant step backwards, basically, because lasers have been around for a long time, and decades now, and at the same time we're talking about using them in a way that is very different from their original application. What's been the catalyst? How have they changed from those lights that they were talking about, Buck Rogers and shooting the alien spaceships down, to something that is now a potential conduit for high-speed communications?
Excellent question. Originally, in the early days, lasers were first observed from solid crystal and gaseous type materials. And so when you built a laser, the size of the laser system itself was big, literally a couple of meters long. And so that's typically what you saw in Buck Rogers movies. Those are typically the type of lasers that they'll use in laser light shows, etc. Now clearly those types of lasers, while they're truly fantastic instruments and have been able to advance the understanding of light and how it's used, those are really not going to be applicable for real world applications. These things are too big, they're too expensive, they're too costly to operate. You need a major plug like this to plug in the wall. You need water cooling to keep the thing cool. And so the advance has really come in the development of these devices which we call semiconductor lasers. And people are quite familiar with semiconductor materials because these are the things that allow transistors to be made. The early transistor radios from the early 60s. Now we've got silicon electronic components in our cell phones, in our laptop computers, etc. And so once the semiconductor laser was invented, and again, that was invented about 40 years ago, in 1964. Once these things were invented and now perfected, we now have the ability to make these things extremely small and compact, and more important, extremely electrically efficient. As an example, we can run lasers off of a couple of watch batteries. And so as a result of that advance, we now have lasers inside your compact disc player, inside your computer, and with those advances, it really enabled the laser technology to be massively applied towards ultra-high speed information and fiber optic communication. That was a real advance.
Well, we have the technology now at Creo. We have people in our community all around UCF. We have video stores which would like to get their products to us in instantaneous, almost instantaneous downloads. It's all got to be connected somehow.
That's
How do we
right.
go about setting up the infrastructure? Is that the blockade right now?
It sounds like you are so closely related to the field. This is in fact the problem. It's what we call the last mile problem. The major telecommunication carriers have already laid the infrastructure, that's fiber in the ground, or however else they want to do it, but basically fiber in the ground, which connects basically big cities to big cities and towns to towns. The problem is in fact getting, if you will, fiber to the home. This is the problem, and the reason is that it costs a tremendous amount of money to dig up roads, to destroy the current infrastructure to place fiber to connect every house. And so getting fiber to the home is in fact the last mile problem, and it is the most difficult to overcome simply because the major telecommunication carriers don't want to pay that bill, and certainly the consumer is not going to want to pay, you know, tens of thousands of dollars to rip up the road to get a fiber to the house. So alternative approaches are being explored to try to get high bandwidth information to the house. Typically the two approaches that people are using are kind of wireless type connectivity, that's like your dish TV, and the other method is cable TV or cable modem for your computer. But nonetheless, even though those technologies are in fact providing much more information handling capabilities, it's the optical fiber that will basically beat the pants off that. And again, until we come up with an alternative way of getting information to people without digging up the road, we'll still have this last mile problem. So one possible solution for that is what people are calling free space optics. And what we're planning to do in that arena is to perhaps put little laser diodes on the top of every street lamp or telephone pole. And this way we don't have to dig up the ground to be able to get a fiber to your house. So in an analogous way of having a satellite dish on top of your house, you'll have a little like a little mini telescope that will look at the closest telephone pole, which will then have a little laser on it, and that telephone pole will be blinking information on and off, in which your little mini telescope will see, and you'll be able to have a little laser in your house that will blink on and off, that will send information out of your telescope back to the telephone pole, and then the light signals will basically bounce around from the tops of the telephone poles or street lamps all the way to a main central office. At that point it'll go into the ground in the fiber and be connected to cities and towns to towns. And that's the initial approach that we're going to try to deploy to get around the last mile problem and digging up roads for the final infrastructure.
You hit on a key word a couple times during that conversation, and that was money. I mean, no one wants to give up what they've got, meaning the cable and maybe satellite and this type of thing, even for an advanced technology. So where do we go, and how do you go about obtaining the research dollars, you know, following the pathways that are going to lead us to putting those diodes on our light poles? Excellent question.
Typically, as you mentioned, the key is in terms of doing the fundamental underlying research, in terms of just thinking about possible solutions of saying, well, gee, if we do have little laser diodes on the top of every telephone pole, you know, what happens if it's snowing out? What happens, well, not in Central Florida, but what happens if it's foggy? This morning was
or heavy rain.
Heavy rain, exactly. So you must come up with unique solutions that get around these problems. Obviously, if you have ideas for these problems, you then must be able to generate money to try and test these concepts out. So at that particular point, researchers and scientists like myself must write fairly large proposals and take these proposals to funding agencies to try to sell them on the idea that not only is this good knowledge creation, but the ultimate fruits of this research will benefit the public in great ways. And so if we can have this tremendous connectivity for information. This will allow our schools to have better access to new knowledge. And clearly at the end of the day, we all know the strength of the best economy will always start out by the best educated students that we have.
What is the status of that pipeline, the research dollars pipeline? I mean, you obviously have, there's a concept there. I mean, it's out there, here's a workable solution. But what are we talking about in terms of time, and how do you go about beginning and ending the funding process to get us up to that point?
Sure. Well, if you have a unique idea, as I always like to say, you must take the show on the road. So you must go visit your funding agency, whether it's an organization like the National Science Foundation or other organizations like Department of Defense. Clearly, laser technology has important implications for DoD type technology. But once you get your research dollars in, then you try to train your students, come up with mini architectures, little test beds to test out concepts and ideas, and along the way you'll come up with extremely unique solutions, and these extremely unique solutions become the cornerstone for technology transfer. As an example, if you have a unique solution, the first thing you're going to want to do is not only write about it for the scientific journal, but perhaps you'd like to try and apply for a U.S. patent or an international patent. And once you start to develop what I call intellectual property, an IP portfolio, then this starts to serve as the cornerstone for business development. And so once you've done the research, you've generated a core technology platform, a set of patents. At that particular point, you can evolve the technology and try and find a licensee for this information. And at that point, they would take this information and try to manufacture it in a cost-effective way. And most importantly, at the end of the day, what I certainly love about University of Central Florida is that they've established an infrastructure for that, the Ucf Incubator Facility, which has been extremely helpful in taking technologies that have been developed throughout the university, transferring them to a place where they can kind of give birth to these new ideas and new concepts, and eventually turn them into productive organizations that help build the economy in the Central Florida area.
You talked a little bit about military applications, and certainly that brings to mind how there may be some hesitancy on the part of commercial interests to rip up their cables out of the ground and replace it with fiber optic. But certainly the military has a vested interest in high-speed communications and getting all of what they need. They may need to get the battle plan from point A to point B instantaneously. How much stimulus do you get from the government? Is that the likely door that's going to open first to get us this?
Sure, and another very good question. To kind of put it on the table, it turns out that the biggest dollars do come from the Department of Defense, simply because many times their needs are immediate. And whereas other funding agencies, they may have a slightly longer term perspective, and as an example, the National Science Foundation may have a slightly longer term perspective, and they like to see faculty working with industry to develop the technology. So the timeline for the need for that is a little nebulous, a little bit more nebulous, whereas from the Department of Defense their needs are much more urgent, and many times they will in fact award reasonably large research contracts to be able to stimulate the research activity, just because they're working on time schedules that cannot wait for things to evolve, to allow industry to slowly adopt practices. Again, another interesting point that you're really kind of getting at is that many times when major industries are kind of well entrenched in a particular technology, many times they're a little reluctant to bring in new technology, simply because if they are not the owners of that technology, it may allow for adversarial competition, which means less dollars in their pocket. So there's a careful balance between how the research is done within industry versus the way the Department of Defense might want to see research done.
Now, does that mean you have to work, for lack of a better term, behind closed doors? In other words, you're developing things that someone may have a tremendous interest in, but they don't want their competitor to necessarily know that you have an interest in this stuff that's going on over here.
Another excellent question, I tell you. Typically, when you're working closely with industry, they're going to want your interaction with them to be rather quiet. And for sure, nonetheless, during that process, there'll be intellectual property development, patents will be filed. But of course, at the end of the day, you're still allowed to publish the technical papers with the students, etc. From the government's perspective, when they fund you, they actually maintain the right to use the technology however they see fit, because they are funding it. And so with the industrial interactions, yes, they certainly will not want to give you money so you can then take that new knowledge creation that you've been able to develop in the lab and tell their competitors how you've done it. Certainly they don't want that to happen.
All right, well, let's try and reveal just a couple of secrets, at least just some capsules of what's going on at the University of Central Florida. Can you give us a broad idea of just some of the different things that you and some of the other scientists are working on right now at UCF that we might see 3, 4, 5 years down the road?
Sure. I will start with my area first because I know that the best, and I will then dovetail off to other research faculty. In our group, we're working on a variety of technologies. One, obviously, is clearly working with the semiconductor laser to make it better for telecommunications. And this terabit per second laser that we developed, the key feature there is that what we relied on is, instead of just trying to turn the light on and off as fast as we can, kind of like light on, logic 1, light off, logic 0, we're kind of dovetailing off of the way radio communications is done. That is, in your basic car radio, if you want one set of information, you tune the dial to a specific frequency which carries information. If you want some different information, you tune to a different frequency. Like this is channel 68. People watching this show will maybe have their dial tuned to channel 68. So in the fiber optic world, what we do is we send information with one color. And if you want to send more information down the fiber, what we use is a slightly different color. And that concept, what we call wavelength division multiplexing, has been really exploited now for about the past 8 years. And it's really taking off and has revolutionized fiber optics. But the challenge has been is that many researchers have been using different lasers, each one with a different color. And at a point where you want to have hundreds to thousands of different colors in a particular optical fiber, using one laser for each different color gets to be extremely cost ineffective. So what we did was we, in fact, were able to show that we could generate 168 different colors from a single laser. And normally lasers like to give just one color. And so when we first started this research, you know, again, being what I call the traveling salesman that we are, you go around to the funding agency and said, you know, we're going to generate multiple colors from one laser. And the funding agents say, we just don't think this is going to work. And so at the end of the day, when you really show that it can work with maybe 2 or 3 or 4 wavelengths, they say, you're on to something. Then you can get good funding. And at the end of the day, we showed 168 channels. Each channel was transmitting 6 billion bits of information. So 6 billion bits of information with 168 colors turns out to be a trillion bits of information per second. So that was one thing we're doing. We're also working on developing new types of lasers that will allow really simple tattoo removal without having pain for the patient. It'll allow for efficient cleaning of teeth, again, without doing any damage to the teeth. We're also working on novel methods of communication which would allow information to be sent in an encrypted way, so that in case anyone were trying to tap the fiber optic lines, they would basically look at the light and say, this just looks like noise, there's nothing there. So those are the types of things we're working on: telecommunications, computer interconnects, some medical applications, etc. Now, other researchers at Creole are doing research in a broad arena, literally from making new types of novel liquid crystal displays that you could literally have mounted on your glasses, as an example. This way you could not only talk to a person, but at the same time have perhaps an image projected onto your glasses, which might be that of a computer screen, and by then moving your eyes around, you could look in the lower corner of your glasses to that start icon that we're all familiar with, and up would have a pop-up menu, and then your eye would move to a different point on your glasses, and these little cameras would track this eye movement, and you'd be able to then literally walk about, and the thing I always like to say is you could potentially think of someone, and automatically they would appear in front of you. And so the way that technology works is, again, you would then use your eyeball to look at a portion of your eyeglass as a start menu. The pop-up would come. You'd raise your eye to your phone list, and then another pop-up menu would come out. And again, these little cameras are tracking your eye movement to know what part of your glasses they're looking at. Your phone menu would come up. You'd go over to the phone number of your mom or your dad or your son or daughter, and maybe you'd blink your eyes or do something cute, and then all of a sudden there'd be an instant video connection to these people, and their image would be projected on your glasses.
Of course, then you have a whole new privacy issue. You'd have to be careful what you think as you walked around because someone else might pick that up.
That is correct. That is correct. So people are working on novel types of displays. People are working on technology that will allow the fabrication of electronic microchips to get down to the atomic scale. People are working on technologies that will allow you to image inside the body with much higher accuracy than ultrasound, and without using ionizing radiation like X-rays. So by using light, you'll be able to see inside of the body with extreme resolution without causing harm, which prolonged exposure to X-rays would do. So those are just some of the technologies that people are working on: novel displays, biomedical applications, applications towards making electronics work much faster because the components can be much closer together, as an example.
From eyes to ears to subatomic particles, it sounds like you guys have your fingers in a little bit of everything out of UCF.
That's right. I always like to say we do research in the electromagnetic spectrum from darn near DC to well beyond daylight.
Fascinating. Well, I appreciate you so much for coming out and joining us today and sharing just some insights. And we've got to have you back. And it seems like if we don't get you back every couple of months, the world may change just there on campus.
We're working at light speed.
Okay, very good. Thank you so much. And of course, that does it for another edition of Profiles. Our thanks once again to Dr. Peter Delfyett from the UCF School of Optics and Creole. For the UCF channel, I'm Ed Highland. It was fun stuff. You have some wonderful stuff. Yeah, now we've got